David Bohm and Basil and a few other characters used to get together, and we had wonderful talks about.
Those were amazing days.
They were, yes. No, it was very, very fruitful and interesting and
Controversial.
Well, I want to talk about where my own ideas have developed since then. I'm afraid that what's new in the talk is in the last few minutes or something like that, because I have to. I'm sure I can't assume that people here are familiar, very familiar at all, or at all familiar with twistor theory, because this is what it's about. It's about twistor theory and a problem which has been confronting the theory for, I don't know, 40 years. And twistor theory was still sort of...
Well, I like to claim that I persuaded you to spell the word twister O-R rather than E-R.
A great contribution.
That's my
I think you'll realise it's a great contribution.
I don't remember that, but I take it away.
I remember it.
Well, here you see.
Because I didn't know what the hell you were talking about.
Well, maybe you'll get it this time.
Yeah.
Anyway, this is what it's about, twistor theory. And I think it's very much stimulated, at least one of the big stimulations behind it. There are a lot of different motivations. But one of them was the idea that, in some sense, physics ought to be described fundamentally in a non-local way. So the non-locality of these sort of Bohm-type EPR experiments was very much in my mind when this idea was being put forward.
Roger, did you have this idea before you met Bohm, or was it simultaneous? Or?
I think, well, the twisters were already around then, weren't they? I think it was before I went to Birkbeck.
Before you went
to get the dates right, yes. When was the Kennedy assassination?
63.
63 was it?
Well, you were here then, at Birkbeck.
It was Birkbeck.
Were you at Birkbeck then? I was at Birkbeck in 63.
You were?
Yes. And David was there as well.
Yes. I'm sort of thinking maybe the year after, but yes, it was probably... Let's not
worry about that.
You see what old octogenarians do when they... You see, I'm using this old-fashioned gadget here, which is showing me to be an old-fashioned person. But then since we're both octogenarians now, get away with it. Okay, here is basically the basic correspondence. We have space-time here, which is initially Minkowski space. That's this M here, which means Minkowski space. And rather than the point being the fundamental object, the idea is at least first to think of a light ray as the fundamental object. And therefore you're driven to think of a space of light rays. This is the space Pn, as I'm calling it. And the point here represents a light ray. And then if you want to know what a point in Minkowski space represents, you think of all the light rays through it, and that's a sphere. But the thing about the sphere, and this is really an important driving force behind it all, is that sphere can be thought of as a Riemann sphere. That means it's a conformal sphere. Well, the motivation is think of a point in space-time, and you think of looking at the sky, and you see stars in the sky, and if you think of the space-time picture of that, that's our past light cone intersecting the world lines of these different stars. They could be, in this case, 4 points on the sphere. And if a different observer was looking at the same sky, because of aberration effects, the sky will be distorted in a certain way, but in a very nice way. It's a way in which it's conformal. Angles are preserved, and cyclic. You have 4 stars that just happen to lie in a circle. According to one observer, they will be on a circle in another observer. And the idea is to think of that sphere, not so much as a conformal sphere, but as a one-dimensional complex manifold. So you're using complex numbers, and the complex numbers are the natural thing to use if you're thinking about quantum mechanics. So I should say that a lot of the motivational ideas behind twistor theory, there's a slight danger of putting things down here. There's a wind blowing out, which could probably blow everything onto the floor. But it's one of the ideas behind twistor theory is to not to try and quantize gravity. That's never been the idea behind twistor theory, but to try and kind of realize features that are common to both quantum mechanics and relativity and bring them together in a certain way. And you're not changing any theory at this stage, but you're looking at things in a way which is, in some sense, influenced by quantum mechanics. And we'll see that later on. So this complex sphere here is a good thing to think about if you're thinking about quantum mechanics, because if you think about, say, a spin half particle, then the different directions in which you can spin, thinking of these as the different combinations of up and down or whatever other directions you like to think in terms of, and then the different linear combinations of that give you an arbitrary direction on the sphere, and that direction can be easily obtained by thinking of the u to be the ratio of these two numbers, and then u together with infinity, complex numbers together with infinity give you the Riemann sphere. So this is the Riemann sphere obtained by stereographic projection from the plane here, which is the complex plane from the south pole, and the place where it hits the sphere here gives you the direction of the spin. So this always intrigued me very much, that somehow there's a special relationship between the three-dimensionality of space and the quantum use of complex numbers, which is very explicitly revealed here. And you don't see anything so nice as that when you go through higher dimensions. So the idea here is to think of this as a complex one-dimensional space. It's a projective space, obtained simply by the ratio of two complex numbers, one-dimensional complex space, and to think of this as a complex one-dimensional space. So what we'd really like to do is to think of the whole space as a complex space. Now you can't really do that at this stage because the whole space is five-dimensional. Just count how many dimensions there are for light rays. 5 dimensions, it's got to be an even number of dimensions in order to be a complex space. So you will have to expect that somehow this 5-dimensional space sits in a 6-dimensional space, and in fact that's what we find, that there is a 6-dimensional space which is a complex manifold. It's in fact a complex projective 3-dimensional space, it turns out. And this is the idea. It's crystal correspondence which brings together this celestial sphere and the complex sphere of directions according to spins, and actually makes this space into a complex manifold. So that's kind of nice. It seems like a bit of a miracle that it works, but there's more to it than that, because if you think, say, instead of just the projective space, but the vector space which it comes from, so here we have now the vector space, that's the zero of the vector space, and the complex rays through that origin give you the points of the projective space. And when you're thinking about twistor theory, it's really this vector space, which is the algebraic thing that you work with. If you think geometrically, it's quite useful in terms of the projective space. Now, a bit of a miracle here comes in, because you can actually interpret the points in the top and the bottom half, which don't lie on here, as spinning actually massless particles with spin. I'm not really doing quantum mechanics when I talk about spin. I'm talking about a massless particle which has a velicity, and I'll say a little bit more about what that, how you get that. But the idea, that's why I put a little twist on the lines here. The points up here and the points down here are both represented by these, or both represent the structure of a spinning massless particle. Now, that's all very well, but the idea that I want to describe today is a generalization of this picture. It looks a bit like that, in the sense that you would say it looks like anything, which I'm not sure about. But it happens to be a non-commutative geometry, and that's the thing that we were discussing before in the discussions. It's what I call palatial twistor theory for a reason which I won't go into here. But the idea is if you want to describe a space-time, not Minkowski space, but a general curved 4-dimensional Lorentzian space-time, it seems that you can do it in twistor theory, but there are a lot of conjectural aspects to this. But you have to be driven to an idea which is fundamental idea which comes from quantum mechanics, namely that you have a non-commutative algebra. And this non-commutative algebra, or non-commutative geometry, as you can say here, is the twistor geometry which still survives when you talk about the curved twistor space. And I want to indicate where the sort of issues come from here, why we are driven to this. But before doing that, I need to say a little bit more about twistor theory. So we have this picture again, and now let's be a little bit more explicit about it. The idea is that you use, say, Minkowski coordinates for the space-time, that's the t, x, y, z, and you use the projective complex coordinates Z0, Z1, Z2, Z3 for the projective space, and the ratios of these will give you the coordinates for the projective space. Now, what gives you this correspondence is the incidence relation, which is just this matrix equation here, where the orange coordinates correspond to the Minkowski coordinates, and the purple ones the coordinates over here. And incidence over here is interpreted by the point represented by the orange coordinates lying on the line represented by the purple coordinates. And over here, it's the point represented by the purple coordinates lying on the line, complex line, in other words, the ring and sphere, described by the orange coordinates. So you have the interpretation between these two spaces given by the incidence relation. In order for this to hold for real coordinates x, y, z, and t, we find that you have this equation here. This is the equation of Pn, that is the Pn stands for projective null twisters. These are the space with the light rays. So you need a real equation to get you down from the 6-dimensional projective space to the 5-dimensional space which represents the light rays. So that is the description, that's how it works. I want to say a little bit more about this correspondence, what it means physically, but first of all, it's really something about spinors. So the twister, Z, we tend to use the word Z for a twister, is really a pair of spinors. I'm calling that omega and pi. Pi gives you the direction of the light ray, in fact the momentum of it. So if I take the two-spinner pi and its complex conjugate times pi, the momentum. You don't know these things, I'll just rattle through them. I'm going to go very quickly through twistor theory, and I hope just to give an impression of it. It's not something you know about, don't worry too much about the details. But you can, the omega is more like an angular momentum thing. The pi tells you its momentum, which way it's going, and what its strength is, what its frequency, or its momentum is. And the omega gives you the angular momentum. Well, it's together with pi gives you the angular momentum. But in the picture here, if it's a null twistor, you can think of the way this light ray intersects the light cone of the origin, and then the omega points along the light ray which intersects that line. So you can see geometrically what the omega and pi mean in the case of a null twistor. To be more explicit, you have to talk about the two-component notation, and I should just flash this out to you because I'm not going to go into the details of this, but I will show you equations using this notation. It's unfortunately not too familiar even among physicists. It's a very good notation, introduced basically by Van der Waerden to describe the Dirac equation and things like that. I do want to say this one thing though. A single index spinor represents, by multiplying by its complex conjugate. I should say you have a prime on the index when you take a complex conjugate. These are the capital letters are two-dimensional indices, and it's a prime, that's a complex conjugate. You need one of each to get to a tensor index or a vector index. Now this is automatically a null vector pointing along the light cone, but there is a phase that you lose here, because if you multiply that by e to the I theta, and this by e to the minus I theta, you don't see it of course. That phase is interpreted as a little flag plane through that light ray. Here is the geometry of it. Think about a three-dimensional slice through that light cone. You get a sphere. That's the celestial sphere, basically. Sphere. Here's the point representing the direction of n, and the flag plane is given by a tangent vector to this sphere. It's, if you go all the way, rotate it all the way around once, you get minus the spinor, and then multiply, rotate it again twice, you get back where you started. So it's a two-value. Okay. Now here's a lot of formulae, so that's just basically the formulae which I've been describing to you a little bit more explicitly. The point I want to bring up here, that's the incidence relation again. The Z alpha has one with an index upper unprime, and the other with the pi has an index lower prime. Incidence relation again. This is what happens when you move the origin. When you take a complex conjugate, you have to swap them around. So this becomes a dual object with this, with the indices appropriately arranged in the opposite positions. And ZZ bar is this Hermitian quadratic form, which I had written down right before. Here. That's that equation. It's just in this notation, just ZZ bar. So Z bar naught, the norm, if you like, of the twister, gives you, if it vanishes, it gives you the light ray. But it gives you more, and here is the correspondence. You see, if you have just the P, the momentum is obtained from a single index twistor. That's the pi times its complex conjugate, which is P. You've got a phase in addition, but you're actually talking about the momentum vector. The angular momentum, you've got to bring omega and pi, these round brackets for the symmetrization. This epsilon is the basic skew metric thing. I will say something about this equation. This is the Pauli-Lubansky spin vector, which is given by this expression, skew symmetric epsilon here. And the thing is, the Pauli-Lubansky spin vector has to be proportional to the momentum. That's a standard condition for massless particles. And the ratio of this one to the other, in other words, S, Pauli-Lubansky spin vector equals S times P. This S is the helicity. That's a real number. It could be positive or negative. And it's telling you the amount of the spin of the particle about its axis. So that gives you a very nice geometrical interpretation, but these are slightly complicated relationships, which in ordinary notation have to be satisfied for a massless particle. And you see with this prescription, they're automatically satisfied by the twistor. The only thing you have to say is pi is not 0, but apart from that, this is, and apart from the fact there's a phase also, this gives you very specifically the momentum and angular momentum of a massless particle. Okay, that's all classical, and that all works fine. However, if you want to do quantum twistor theory, which you might call first quantized twistor theory, and you can look at the commutational rules between X and P, that's from standard quantum mechanics, and you see that they're very closely related to these very simple commutation relations here. The twistor, Z, commutes with itself, that is, Z alpha, Z beta, doesn't matter which way around you write it, similarly with the Z bars, but Z and Z bar are canonical conjugates. So 1 times the other minus the other times the 1 is the Kronecker delta, and that's the reduced Planck's constant here. So that they're not just complex conjugates, they're also canonical conjugates at the same time. Now you write your momentum and angular momentum expressions, you find that there is no factorial problem because of these round brackets. So that works fine, they work just as well as before, and you find that the commutation rules that you get from the standard quantum mechanics of angular momentum, generators of the Poincare group, are completely false.
Can I just ask a question, Roger?
I'm sorry?
Can I just ask a question?
Of course.
Have you defined what have you pulled in from outside that symplectic structure that you've got? Or does it come out naturally from the structure?
Really. I mean, first of all, it's just, okay, we postulate this, and then you see that the ordinary X and P's have the right commutation rules, and you get the right commutation rules here. But it's also something which is naturally related to a symplectic structure. It's the one you refer to.
Yeah.
And actually that's where it came from. You start from a symplectic structure which is conserved when you introduce curvature, and that symplectic structure, I'll come to that, but that's right. When you say you quantize, say that symplectic structure, the symplectic 2 form should be, or crossing brackets if you like, they correspond to the commutator. It's exactly this. Yes. So there's no real choice about what you write down here. It's very natural. Now, this leads you to a notion of a twistor wave function. Now, you see, if you're thinking of a twistor wave function, just with like the ordinary quantum mechanics, you've got X and P, they're canonically conjugates, so you can write the wave function in terms of X or in terms of P. And if it's in terms of X, then P becomes d by dx, and X becomes d by dp with i's and minus signs and things. Okay, here, Z and Z bar then are canonical conjugates as well as complex conjugates. So you want to say, what is a wave function? Well, it's a function, say, of Z, which is independent of Z bar. What's independent of Z bar mean? It means this equation, partial d by dz bar equals 0, and that is the Cauchy-Riemann equation. So it's telling you that the function f is holomorphic, or complex analytic in Z, which was very nice from my point of view, because one of the driving forces behind the whole theory was, to me, the power of complex analysis. I remember when I was an undergraduate, quite astounded by complex analysis and how many magical things come from that. Much nicer theory than real analysis. Complex numbers seem to force you into all sorts of wonderful mathematical theorems, which you wouldn't have guessed otherwise. And it's
Can I ask another question?
Okay, go ahead.
Where's the quaternions? How do you look at the quaternions?
Well, you can think about quaternions. The trouble with quaternions, I mean, they also form a very beautiful algebra, but it's not, that's nice in algebra, because they're cute, and because there's no notion, as far as I know, which makes really good sense as an analogue of holomorphic. The problem is, in quaternions, is you can algebraically express the complex conjugate in terms of the original quaternion. So the complex conjugate is not simple, is not sort of independent of it anymore. And there are ways, I know people have tried to make notions of holomorphic for quaternions, but it's not nice. You don't, as far as I know, get the sort of magic that you do get from complex numbers. But yeah, it's a reasonable question. Okay, so our wave functions are going to be holomorphic functions. Now you might say, what's the helicity? The helicity is this expression. I don't think I quite said that last time. If you right, you see here is the helicity. The only thing it does, you do have to worry about when you worry about the commutation rules. I'm not sure if it's on the slide here. You see here that these go out without any worry about the factor ordering. But the helicity you find you have to be careful. And it is this slightly shifted expression. So you have z d by dz as the helicity, but it's shifted a bit. This is the Euler operator. The eigenstates will be homogeneous functions. So it's, again, homogeneous functions, which will be the eigenstates of helicity, but you have to worry about this shifting. All right, and so here we are. N is twice the spin, and I like to have the spin as for the number which characterizes being an integer rather than a half integer. So for a photon, the number would be plus or minus 2, and for a graviton, plus or minus 4. And the degree of homogeneity then is minus 2 minus n. And then you find then a twistor wave function ought to be, because here you could do it with the dual ones if you like. That's just like going from position to momentum. Equivalent representation, but you have to make a choice at some stage. Now here are the different homogeneity degrees and the relation to the various massless particles you might be interested in. There's a massless scalar, it's homogeneity degree minus 2. For a photon, minus 4 for the left-handed, plus 0, or 0 for the right-handed. For a graviton, minus 6 for the left-handed, and plus 2 for the right-handed, which looks a little lopsided. If you go to the dual description, they rearrange themselves the other way around. But it's this lopsidedness which plays a big role in what one used to say. Now what does that do? How do you write the ordinary equations? Well, there's a nice way, basically due to Dirac, which tells you how you write the equations for all spins. And you just have spinors with lots of indices, they're all symmetrical, and then you write down the simplest wave equation you can, and this gives you the massless field equations. If it's got no indices, now there's a scalar, it's just the down version acting on it. This is the flat space. And the relation between the Maxwell tensors, you just construct the self-dual parts by throwing in some epsilons, and then you get the Maxwell tensor. Well, here you get the linearized gravitational field. This is the linearized curvature in vacuum, or the vial curvature in vacuum. And the equations are just these things down here. I'm not going to go into details here, but these equations are exactly what you want, and you want to see the relationship between these equations and these homogeneity degrees. The relationship is attained very elegantly by means of contour integral. Let's look at it in the case of a scalar field. I should make a point here, because if you're thinking about wave functions, which I am thinking about here, then there's another condition which you might want to impose. In other words, the condition that it has positive frequency. Now that this is just a point about twistor geometry. You see, to say something has positive frequency, a nice way of saying it is that it extends, your function extends into the complex, to complex points, where those points in the cosmic space have imaginary parts which point into the past. So this is what's called the forward tube. The forward tube is that part of the complex in the cosmic space where the imaginary part of the position vectors points into the past. Now that the correspondence here is complex points together with the lines that you get. I should say that you see for a real point, that's where the imaginary part is 0, you get a line which lies in P, and that's the Riemann sphere that we started off with. These are projective lines, they are just Riemann spheres. I have a problem, how do I draw it? You see, do I draw it as a line or as a, sometimes I draw it as a sausage, you see, it's a sphere and a line at the same time. But anyway, that's the Riemann sphere. If it lies entirely in Pn, it's a real point. If it lies entirely in the top half, then that's the forward tube. So the forward tube, in twistor theory, is really the top half of twistor space. And if you say your field, your wave function extends into the top half, that is the positive frequency condition. Now how does that translate into these functions here? That's the right one. Yeah. Here we have the contour interval. Let's take the scalar case first. This has degree -2 for a scalar. We have a form here which is of degree +2. That cancels out the -2, so this is homogeneity degree 0. It's a good, well-defined thing on projective space. You then put in the, see this is a function of omega and pi. You get rid of the omega by putting the incidence relation in. That changes gets you the function of pi, and x. The x is the position. Now that pi is what comes in here, so you then integrate out the pi dependence and you get something with an x dependence. So that's the idea. That's how you get a solution of the wave equation from the twistor function. But more explicitly, let's think of the simplest sort of case. What you can think of is a function which is a reciprocal of the product of two linear forms. These linear forms vanish when A lies up. There's a plane A and a plane B where it's vanished. Here's the plane A, here's the plane B. As long as they intersect in the bottom half, then you can be sure that your line in the top half intersects these places. Those are the singularities of this function. Intersects the singularities in two separated points. There they are. This line is the Riemann sphere here. This is your contour integral which goes around separating those 2 points, and you have a good answer. So this gives you positive frequency fields. It gives you them all, in fact. It's a very convenient description. However, there's a little issue here, because you might say, suppose you add lots of these things together, it's a bit awkward to have these singularities lying around, because they'll kind of spread themselves all over the place, and it's an awkward description. See, there might be big blobs of singularity like that. Before I get to that, you can generalize this very easily to spin other spins by just putting a lot of pi's in there to get you the ones with prime indices. Those are the right-handed ones. The ones with a lot of d by the omegas. Now, why do I say d by the omegas? You see, this is a hint of this quantization rule. I'm not really using it, but suppose you say, you know how to do the ones with the prime indices. How do you do the ones with the unprimed indices? Well, you take the complex conjugate. But you can't take the complex conjugate and keep this homomorphic, because if you do the contour integral, you've got to have homomorphic functions. So what do? You don't take the complex conjugate of pi, you make d by the omega, which the twistor commutation rule suggests. So it's quite a natural thing to do. I'm not really using much quantum mechanics here, but I'm using the commutation rule in this more or less classical way here. That's just an aside point, but it's interesting to see that this commutation rule is already playing a role in lots of things that we've been doing for a long time. Now, to get around this little issue of this, it looks very non-covariant. If you rotate something, these planes A and B will go all over the place. How do you make it look more covariant? Well, what you do is you reinterpret this camel function. You see here I just smeared it a bit, so if I rotate it a bit and add them together and integrate them up, I'm going to have 2 singularities which are just great regions like this, which I hope to keep separate. If I can keep them separate, then I can still do my contour integral. But it's best to reinterpret that picture. This was something I basically learned from Michael T. We had lots of discussions in Oxford about this. What you think of as the region you're interested in, where the function is defined, is this top half of twistor space with 2 camel humps taken out of it. Now the right way to think of that space is the intersection of 2 regions, each of which has 1 camel hump taken out of it. And the union of the 2 regions is the whole space. So the space you're interested in is covered by 2 open sets, whose intersection is where the function is defined. And it turns out this is just an example of what's called sheaf cohomology. And I don't want to go into this in detail, but just to give you the rough idea, this is the case where you have a space and you cover it with a lot of open sets. But what I've done is where it's the only two open sets, which is the simple case. And if you have lots of them, you can have lots of intersections of pairs, so you have lots of F's. This is where the functions are defined on the intersections. Lots of intersections of pairs, they have a condition on triple intersections, and they have the property that you're not interested in things which can be expressed in terms of functions which are completely defined on one open set or the other. So you factor out like these, and then you get an element of sheaf cohomology. I'm not going to go into the details of that, just throw it at you really. So if you're not familiar with it, don't worry too much. But the point is that it's a very useful concept in complex manifold theory and things like that, and it's mathematically it's been studied for a long time. And I hadn't realized that's what these functions are. They're kind of elements of first cohomology. And one of the big initial motivations of twistor theory was how do you express if you have a function on, this is the Riemann sphere again, that's the real axis, these are the real numbers with infinity going around there, and this is where the imaginary part is positive or negative, whichever round it is. And you have the positive frequency functions, the ones which extend holomorphically into the one hemisphere, and the negative frequency into the other hemisphere. That picture has attracted me a lot, rather than saying the condition you do Fourier analysis and then you take those with positive coefficients and so on. It seems to me was a much more geometrical and analytic way of saying all that. And this does it, because you can do it locally for a single number, but I wanted to do it globally for the whole Minkowski space. And that does it here, but you're splitting this now into the top half of twistor space and the bottom half, where you're talking now about first cohomology that's describing your wave functions. So the wave functions, they're not quite functions in the ordinary sense. They're these cohomology elements. Let me say a bit more about what that means. There was a construction which I had, I'll do this one here. Once you realize that these functions are sort of patching together spaces, you can do something more with that. You can say, suppose you paint your function on overlaps, and with this condition on triple overlaps, consistency condition. And then last night you paint them with some paint. In the morning you wake up and you have a look at it, and the paint is dried, and it's sort of crinkled up the space. So the space you've got now is now curved. That function is acted actively on your space to make a curved space. Now if that was a piece of twistor space, you've curved up your twistor space. And this is an important idea. It's the linear function that you have, which was your cohomology element or your wave function, is now acting on the twistor space itself. It relates to a subsequent construction made by my then student Richard Ward, where he showed how to do bundles and got the Yang-Mills fields. This is to do Einstein equations, and this is to do Yang-Mills fields in the same way. I won't say too much about that, but it was a very important construction in the theory. I'll say more about the Einstein case. So you want to construct, first of all, back to Minkowski space, let me make a point here, which I don't think I said. So here you have the points in complex Minkowski space now, represent lines in this complex projective free space. When these points are null separated, so you lie on a light ray, it means these two lines intersect. So incidence over here is translated into a bit of the Lorentzian geometry over here, although it's all complexified. Now, what I'm going to do is to deform my twistor space, and this is a sort of local construction. It's local in space-time, which means that in the twistor space, what does the neighborhood of a point mean in space-time? And the point is represented by this line, or Riemann sphere, in our projective space. And then you say local, that means take a little neighborhood, that's a tubular neighborhood of that line. And what I'm going to do to that is now break it in two. Remember that line is a Riemann sphere, and it's got, imagine it's pieced together with two extended hemispheres with a little band going around them like that. So this is a thickened out version of that. And so now that's what this is. That's the two pieces of the Riemann sphere. And then I push one, I just deform the space by a finite amount. So I sort of slip it like that. And so the line which I had before now is broken. It's no good anymore. But then you appeal to a good, wonderful theorem by Kodara, which tells you that if, as long as this is, could be a genuine finite displacement, as long as it's not too big, you can be assured that there will be another line close to the one you started with, which is defined, it's there, and also the family of these lines is four-dimensional. So it's really rather remarkable. This is the things you get from homomorphicity, the complex analyticity. This is your kind of rigidity. You might think these were real curves, you could bend them any other way, but with the holomorphic condition, you can only bend them in a restricted way, which gives you a four-dimensional family. I should say that a lot of these ideas came from a construction due to E.T. Newman, Ted Newman, which influenced me a lot in his thinking. But then you say, okay, you've got this curved twistor space now, but then you say the same thing. If you get two of these deformed lines now, if they intersect, that means null separation. Therefore, you have a complex conformal structure here. It gives you a complex conformal space-time. Conformal meaning you've got like cones, but you don't necessarily have any notion of metric. And this is the way of getting the Einstein equations. I'll say that in a slightly different way, which is a little bit more general. But to do that, you see, the constructions have just so far told you what null separation is. So it tells you what the like cones are in the space. If you know your twistor geometry, you know what lines meeting means. That means you've got like cones. This is all complex, really. Now, if you want to know a distance, if you want a metric, you have to introduce another notion, which is what I call the infinity twistor. The infinity twistor, we can now generalize what we used to have in the old days, because we believe that there is something like a cosmological constant.
Are you essentially fixing the light cone as infinity? Can you do that?
Yes. But the light cone at infinity is there in Minkowski space, and that is what's given by this object. This is the infinity twistor that describes it. But in de Sitter space, which is the generalization when you have a lambda cosmological constant, it's not a light cone as infinity, it's a space-like surface as infinity. But if the cosmological constant is positive, it's a space-like surface as infinity. And that is given by this infinity twistor. The infinity twistor has these, its complex conjugate is dual, but the point I want to say here is if you contract it with its dual complex conjugate, you get the cosmological constant. If that is zero, then you get the light cone as infinity is defined by this I thing. I didn't stress that point before, I didn't even mention it actually, but you're right. There are those light rays which are at infinity in Minkowski space, which are all part of the picture, and I didn't take the trouble to mention them. But now I have to mention them in a sense because they are included. In the de Sitter case, you don't have null lines to infinity, so you don't mind about that. But you do have a metric which is fixed once you have this I alpha beta. Now this thing gives you a complex symplectic structure to space-time. I'll come back to this. It's not the symplectic structure we talked about before because that's a real symplectic structure. I'll come back to these things. But this gives you a complex symplectic structure. If you have a non-zero lambda, if lambda is zero, it's a kind of degenerate symplectic structure.
Does that give you the real structure then, when the constant?
It would be a real structure if this was real, if you were talking, if you were using the null twistors and so on. Yes. Yes. That's right. There's an interesting point about that. But let me use these things in the performing of the twistor space. This gives you a slight generalization of the construction which I had before, which I referred to as the nonlinear graviton construction, which is this one here. That construction does generalize a bit. See, I'm actually, in principle, using the I alpha beta to do a projection, which you need to have. You need to preserve that. But it's better to say it this way. This is an infinitesimal deformation. So you have a twistor function, homogeneous at degree +2. Then you take the derivative, and this contract it with the infinity twistor. This now gives you a vector field which is on the projective space. Its homogeneities cancel out, and so it gives you a vector field on the projective space. And this vector field gives you the deformation that you want to make between the two patches, giving you a curved twistor space. So this is just the same as I said before, but it's phrased in terms of the infinity twistor. And that allows you to generalize to a case when you have a cosmological constant. This was a construction that Richard Ward worked out in more detail and showed that this does work indeed. That's fine, all this is fine, except that it only works when this f here is homogeneous of degree +2 to get the zero homogeneity here. Degree +2, that's the case of a left-handed graviton, if you like. It's a complex space-time. It's not a real space-time because the Weyl curvature is necessarily anti-self-dual. That means that if it's a real space-time, since the self-dual part is necessarily the complex conjugate of the anti-self-dual part in a Lorentzian space-time, this means that your space will necessarily have no Weyl curvature at all if it's going to be obtained by this construction. So it's got to be conformally flat and therefore boring if it's got to satisfy the Einstein equations as well. So it's boring. It's not only boring, it's a real obstruction to twistor theory. And this is what I call the googly problem. You see, the googly is the ball.
You're bringing on the off break now, are you?
Sorry?
You're bringing in the off break now, are you?
That is the off break. Well, that's actually, I was calling it the googly rather than the off break because you're using the same action. You see, the leg brake is the one which spins left-handed, and that's the one we know how to do. So the googly is they use the same action. You're not changing to a different action. You're using the same twistor space, but you're bowling it so it spins the other way, which is why it's called googly, you see. And it's hard to do, which is another reason why it's called googly. Okay, you could call it an off break, but I think the googly is stuck in all this. So what we call the googly problem is, okay, we know how to produce what we call left-handed gravitons. You see, it's all right if you don't want to construct a real space-time, but just a complex space-time-like entity. And I call it a nonlinear graviton, thinking of it as a graviton in the sense a single graviton ought itself to contain nonlinearities. It would not be appropriate really to think of a graviton as a linear object, although people do. This is the normal practice in physics. But I'm going to say, no, we should think of the single graviton as being actually a nonlinear object. So that's why it's called a nonlinear graviton. But it's nevertheless necessarily left-handed. It doesn't spin right-handed. And that was the whole problem. Okay, you can go over to the other formalism, you can go over to the off-break formalism, and then you can roll the other one. But the idea is that
So how do you choose between the two? You've got
they're
both there in the mass.
They're both there in the mass, and you can choose one, and you can choose the other, whichever way you're stuck. That's the idea. Sure, nature might herself say, yes, secretly I prefer one, and you don't know yet which it is. Maybe that's the case. In fact, I sort of think that. But
maybe it doesn't prefer the one.
well,
and then you're going to get to the idea that David Bohm was talking about, which was the different explicate orders.
yes, well, that's a good question. I mean, what I'm going to say doesn't actually pick one or the other helicity. It's just a point of view. But I mean,
I just wanted to make sure it was there in the mathematics and you hadn't
Yes.
gone away for some assumptions you made.
well, I think it's there in the mathematics, but you have to broaden the picture that I had before. I mean, okay, say in a minute what you're saying, and maybe that will help the discussion. But yeah, so what we have is left-handed nonlinear gravitons. We don't have the right-handed ones, and we certainly don't have a way of piecing them together. Now you see, for a long time, I kept trying to do this construction, googly problems, by saying, well, you go up to infinity, and then the structure gets simpler, and it does indeed. But if infinity was null, that is if you had a zero cosmological constant, then it was a way of encoding both felicities. I didn't know what to do with it, but I had a way of encoding both felicities, which biased me against the cosmological constant for a while when it was seemed to have been discovered. But I eventually got convinced that the evidence is pretty strong. And so I realized I'm going to do something else. Anyway, going out to infinity didn't seem to be quite appropriate. I mean, you're trying to have a theory which you could use locally, and to have to go out to infinity and then come back again seemed to be a bit excessive. So I started to wonder about whether you could do something else which would give you both handedness at once. And I had this sort of idea which you might piece together a manifold, but where you didn't really have the manifold. You see, if you want to do this piecing together, which I had before, And you want to say, okay, you're piecing it together, but you want to make sure it's a complex manifold when you pieced it. In other words, you want your, if you like, your sheaf of holomorphic functions to agree with it over here. So you know what a holomorphic function is here. That means they've got a match when you go over here. So I approached Michael T. on one occasion. I said, look, I've got this problem and I don't know how to address it properly. And I want to piece together these things without having a manifold. And so he said, well, that won't work, because if you have the algebra, you know the prime ideals and that gives you the points. Well, I sort of knew that, but I didn't want to face up to it. But then he said, but that's not true if you have a non-commutative geometry. So I thought, my God, we have a non-commutative geometry. That's this one.
Yeah.
So if you use this one, and this is the idea, doing just what we did before, that you're piecing together pieces where you don't have a manifold down here, you just have the algebra, the non-commutative algebra of functions. And you piece locally in some sense. Locally is a problem, because I'm never quite sure what locally means in these things. But nevertheless, the sort of idea is this. You piece them together, and then you get a structure, an algebra, which is globally defined, and you can extract from that algebra the various notions you want. So this is the idea which has been floating around for a few years now. The question is what to do with it. I should mention a few points here, which are what's going on here. You see, if you take a local piece of the algebra, there are lots of ways you can realize that as what you would say in ordinary quantum mechanics. You say, you've got an algebra of operators, and you say, take a complete set of commuting operators.
Yeah.
Then you form the functions of those. But then you could find another complete set of commuting operators. And if it was x's and p's, although you have some issues there, it would be take the positions or take the momenta. And you could do either way, and then one would become differentiation with respect to the other, and so on. So it's the normal procedures you have in quantum mechanics. But you could have more restricted systems like that, where you have different ways of representing them, and that freedom is there. Now the idea here is that freedom is what you use to construct something non-trivial. Because you've got different ways of doing it here, different ways of doing it here, but you try to match it in one region, and you find that that matching doesn't work all the way around. That you've got to have that freedom of different complete sets of commuting operators. It's a bit like in quantum field theory, we have the vacuum. I don't think it's quite that. I think the better analogy is to think of a complete set of commuting operators and say, well, you can form your quantum theory one way or another. So to get the structure which is non-trivial, it's got to be such that you don't have a global complete set. It's something which you have to move all the way around. Now this encompasses both.
Is this in any way related to von Neumann algebras?
Yes, I think so. I have a problem, you see, people say about C-star algebras and all that, and I have a problem about saying how your scalar product is defined. There are ways of defining scalar products which have the right property. You know, d by dz is z acting one way, is d by dz bar acting the other way. And yes, it does give you that. You certainly have that. I'm not convinced that the integrals, which basically a formula due to Andrew Hodges, gives you a formula which does takes, it has to be cohomology elements when you're talking about here and here. So you're looking at first cohomology and trying to patch that. So this is a problem which, I expect I've run myself out of time, but let me just make a few points. One of these points was, I was in Mexico a few weeks ago, and I elected to, one of the talks was on cosmology and then something was on twistor theory. And the person who invited me had suggested, this was a man called Ernesto Lupiccio, and he invited me to give 3 lectures. And he said, he realized I was going to talk about some of these things. And so we discussed non-commutative geometries. And he had the philosophy. He said, well, you take these abstract concepts in mathematics, and his philosophy was, well, they may be hard to understand in terms of the way the pure mathematician presents it, but what you really want to do is to have a simple example which illustrates all the features of it. And his philosophy was that you could always find these simple examples. So he started to describe to me what the simplest example of this holomorphic non-commutative geometry was, which is basically a 3-sphere, which you think of a hop-fibered 2-sphere with S1, and you cross that with another S1, and those 2 S1s give you a torus, And then you take this torus and you have a foliation of the torus, which when you go around and around, it never quite meets itself. And then you factor out, and then it gives you a non-constant geometry. I was trying to understand all this, which I still don't think I completely understand.
It's straight out of Alan Common.
Yes, yes, but it's all Alan Common point of view. That's right, exactly. That's where you got it from. But then I was preparing my next lecture, which was basically this sort of thing. No, that was the lecture after that. But then I thought, I don't often describe twisted theory using this picture, because it's old-fashioned. So what does that picture mean? Well, that picture means, that's where the name twister came from, originally. Because you think, okay, how do you represent these points, which are in the top and the bottom half? Well, the first original idea was not the way I'm describing now, because I didn't know it then. But it was the original idea was basically this picture, which corresponded to certain solutions of Maxwell's equations, or more specifically, to certain congruences of light rays in space-time. What are they? Okay, think of a point in the top half of twisted space, or bottom half, but not on Pn, somewhere up here. Its complex conjugate is a plane. This is non-constant geometry yet. It's a plane somewhere. That plane intersects Pn in something which is topologically a three-dimensional sphere. So that three-dimensional sphere is a sphere's worth, the three spheres worth of null lines in Minkowski space, none of which intersect. They twist around in a complicated way. And I figured out what that structure was. Well, it's perfect parallels. This is the picture. Any one time, it's a congruence of light rays. So there's one light ray at each point at any given time. Say time t equals 0. Now, each light ray will be represented as a point with a certain direction attached to that point. That's the way it's going. Okay, take this figure, and at any point there will be a circle going through it. Now that circle will have an arrow pointing. That's the direction of the light ray. It's quite a remarkable construction because this whole configuration travels along there with the speed of light. It's sort of reassembled. It keeps coming apart.
Sorry, did you actually construct that sphere?
Yes. Well, it's Clifford parallels projected, stereographically projected. I knew that construction. I knew that picture already. But it also has a physical interpretation as the angular momentum on momentum of the master's path. I won't go into that, but the evidence of pi is at any point in it. The pi is the direction of the thing, and it only goes the direction of the light ray. Now the thing is, this picture, there is another S1 because that is the flag plane of the momentum vector, which products this. This is exactly the space that he was describing to me. And then you have to imagine it's foliated in this way and you get the non-constant geometry. So it struck me, this is a remarkable thing, that sitting in twistor space, right from the start, was basically this simple non-commutative, the simplest holomorphic non-commutative geometry. I think I have to understand it better. I don't probably understand these foliations and why they, because it doesn't seem to depend, as long as the angle is irrational, we seem to get the same algebra. He said he wasn't quite sure about that. But why should it be irrational or rational? It's difficult to see. I just want to mention about three things very rapidly, and then I'll stop. One of them is noise, which came up before. This is the symplectic structure of light rays, and we do get these. This is the form, dpdx. That's the same in twistor theory if it's null as this dz dz bar. So it is exactly the standard symplectic form applied now to light rays. And if you try to quantize, geometric quantize with respect to that, and this is interesting too, you see, if you want to apply geometric quantization, well, what you do is you have a symplectic manifold. The symplectic manifold is the light ray space, but where you have a scaling due to the momentum. So the momentum scaling gives you another dimension, 5 dimensions plus 1 for the scaling, 6-dimensional. It's a symplectic form with a symplectic manifold with a symplectic form given just here. However, in geometric quantization, what you have to do is to introduce a circle bundle over it. Well, the circle bundle is already there. It's this phase of the spinors. So if you take the spinors rather than the momenta, you've got the circle bundle. So it struck me as quite remarkable that there's something very specific, I should say, to three space dimensions and one time dimension. If you got to higher dimensions, these ideas don't work nearly so nicely. But I won't go into the details, but this is what happens with the you try to form a connection on this bundle whose curvature is given by this form. And that connection gives you the idea of, it gives you a quantization procedure which is, it's a bit too, it doesn't give you a unique one if you've got a specific space-time, but that's good in a way because you want freedom in that to make use of in the construction. That's point number one. Point number two, I'm afraid I'm just rushing through these things. What about the Einstein field equations? Well, that's quite remarkable too, because I've known something for a long time which I didn't know how to make use of it. There's a thing called local twistor space. These are defined in any four-dimensional Riemannian pseudo-Lorentzian, four-dimensional Lorentzian space. At any point, you have an omega and a pi, which are conformally invariant objects, and when you go along a curve, you have to transport them according to the equation here. This transport is integrable if you have a conformally flat space. So if the space is conformally flat, you can extend these omegas and pi's to the whole space, and that gives you your twistor space. However, suppose it's not conformally flat, then it isn't integrable. So what do you do with it? Well, you can also introduce this infinity twistor, and what you find is that this infinity twistor, the same object which I gave you before, which is can be defined locally in the local twistor space, it's globally constant if and only if the Einstein vacuum equations hold with cosmological constant, that cosmological constant. So the Einstein equations are the existence of a globally defined infinity twistor, which means that if you could get all the other stuff to work, to make manifolds, how do you construct the manifold out of the algebra, which I can see how to do, I think. You just have local subalgebras, which two-dimensional subalgebras which commute, and these correspond to the points. So I think the notion of what a point is in space-time is obtainable in the algebra. Whether all the mathematics really works is not settled at the moment. However, if it does all work, to state the Einstein equations would be relatively easy. All you do is you say there is a constant I alpha beta. Finally, okay, as this stands, this only gives us real space-times. It's not the quantum gravity theory. It's not a quantum gravity theory, mainly because the Planck length plays no role. We have the Planck's constant in there, but we don't have the Planck length. There's nothing to give you a scale, a metric scale, without the infinity twistor playing. Well, you've got the infinity twistor there, but it doesn't come into the geometry. The geometry is just ordinary Lorentzian geometry, as far as I can see. If you want to make something which actually has a chance of being a quantum gravity theory, and by that I don't mean a theory which is going to be standard quantum mechanics, I think you want something which is more than that, which actually gives you something with a reduction of the quantum state as a feature of it, but that's just waving hands around at the moment. But you can imagine that in addition to this commutation rule we had before, you have these ones with the infinity twistor. Now there's something here of curiosity as far as I'm concerned. I thought of these things a long time ago, ages and ages ago, as a way of extending these commutation rules. But then I fiddled around with it and realized, thinking then that there was no cosmological constant, that these singular i's didn't give you anything new. You could just do a little transformation and you get rid of them altogether, and these just disappear, and these commute, and there's nothing new. However, if you've got a cosmological constant, there's a structure here which, as far as I can see, doesn't go away. And so you do have something genuinely different. Now, it's interesting that people try to quantize space-time by having these non-convexive geometries where the positions don't commute with each other. This is very different. I never liked that procedure because you have some kind of directionality. It's not Lorentzian invariant. It doesn't make too much sense.
We don't have any evidence for
Sorry?
it. We don't have any evidence
There's
for
no
it.
evidence for it. Well, I don't know how much evidence there is for this either. But I am
No,
saying...
right, I mean, okay, I agree with you.
but I agree with you. But listening here at least gives you hope for something with the right kind of invariance and which could possibly be some sort of quantum gravity theory. I would say that another point I should make here is that, see, one of the reasons I was thinking about going on lines like this is using twistor theory to try to describe quantum geometry or the reduction of the states. You see, if you have an EPR situation, you've got whatever it is, I can't remember, 170 kilometres away or something, you know, photon.
I thought it was more like 140, but I might be
Maybe it's
wrong.
100, maybe it's only 140. I think you're right.
It's enough.
Could have gone up by now, but that's right. And so you have entanglements over there, and entanglements over there with over there, and then somebody does an experiment over there, and according to me, the experiment is only made, the state reduction is made, and that means that the space-time has now made a choice between alternatives. And the space-time over there makes a choice when that fellow makes an experiment between alternatives. But then you have a space which is somehow got still until information can actually get, classical information can get from one place to the other.
And don't forget, if there's a storm in the Sahara, this breaks down. Did you know that? I'm talking about Zeilinger's experiment.
Yes, this was the thing which happened.
It doesn't work if there has been a dust storm in the Sahara.
I see. Okay. Well, let's do that in a special case when there isn't.
So I'm just wondering what that means to your collapsing space-time.
Well, they can, as long as you mean the entanglements get.
Yeah, the entanglement gets broken.
Yes.
It's very
if the
fragile.
entanglements get wrecked, you don't have a problem, I suppose. But as long as there
But
are.
how does it fit into the way you're looking at it here? So that's.
I don't think it worries too much if the entanglements get broken at some point. I mean, it could be broken in some other way. And my view is that entanglements do get broken, and they get broken when the measurement is made. Now, that measurement may not be by somebody in the lab. It may be.
You mean the dust in the dust storm?
The dust storm might do it too. Sure. Oh yes, you could imagine that. As long as it mucks up the entanglements, then it's.
But I think there's a question. Yeah, but I think there's a question of exactly what mucks up the entanglement.
Yeah.
Is it mere? What do you mean by measurement?
Yes.
Yeah,
No,
go on back.
I agree. I mean, I don't know what dust storms do, but the idea would be that in many situations, in almost all situations, what happens is that the environment gets involved. So you have a quantum system superposition, a dead cat and a live cat if you like, but, well, the cat is big enough easily that you could have a much smaller thing, and it would entangle with the environment. Now the environment is going to involve the air, and even a slight displacement of molecules in the air will cause quite a lot of mass displacement overall, so the reduction will be in the environment.
So you're still tying it to mass change?
Yes, but I would imagine, I haven't done the calculation, but I would imagine it's quite easy to, if you have a quantum system which is not isolated from the environment, that there will be easy scope for enough mass displacement between the superposed states in the environment for the gravitational criteria to come in and tell you the reduction of the state. So that would be my picture. And the dust storm, I won't do that, you see. So, but of course the idea of the experiment is to try to keep these things down to a low enough level that you don't see any environmental decoherence, and so therefore any reduction would have to be.
So I'm not sure I believe in environmental decoherence.
No, well, by itself it does nothing. I agree. It does nothing by itself, but what it would do is bring the environment into the quantum system, and therefore very likely involve a sufficient mass displacement that the gravitational criteria will come in. It's not as though the environment itself, I mean, losing the information in the environment, and I agree with you, doesn't do anything. I mean, it does something that we can't make use of, but it doesn't do anything fundamentally. It's only when that displacement between superposed states differ from each other enough, which could easily be in the environment, because individual molecules in the air, or whatever it happens to be, quite quickly got displaced, and the totality of them will probably give you a big enough effect. But I'm guessing here, I've never done the calculation.
What did you talk about in some kind of interaction, though, Basil? Ultimately.
I think that's the end of my lecture. We can have some meetings if you like.
Yes.
Especially after string theorists and so on demanded these extra dimensions. One of my main reasons for not liking that is that I like this, you see. And so this scheme would not work. I mean, it's very specific to 3 space and 1 time dimension. It's the only space-time dimensions which you have a holomorphic light cone space.
Can that be formulated neatly, or is it just that you can't find another one?
No, that you can see that they are there. It is the only one. You get a complex manifold for a light-based space. So, I mean, there are others where you have spinors which are complex. You see, it's quite ironic in a way, because the various numbers of dimensions that string theorists like to work in, originally 26 or 25 space in one time, or 10 space, 9 space in one time, or 10 space in one time, or whatever, it was 10 space in 2 times, that was the F theory. All of those, if you look at the nature of the spinors, they're either real or quaternionic. None of them are complex. The only one which is complex that I know, which comes into anything, is the one we have. So that's a weaker condition, because you do get out of...
Do you think this is unique in physics, mathematical physics, in the sense that it hinges on dimensionality?
Well, that's a motivation which I would say yes to your question. But it's a very personal motivation. I don't necessarily see other people having the same motivation. But yes, I always thought that the number of space dimensions and time dimensions needed some sort of explanation. That it's, I mean, you can think of other explanations, like having closed orbits of the planets and so on. That seems to be the kind of explanation. You wanted something more basic and fundamental, and the structures that you get here really are crucially dependent on 3 space and 1 time. You have twisted versions of twisted theory at other dimensions, but they lose out on one thing or another very quickly.
Anybody else? Sorry, I didn't see them.
So you talked earlier on about this twister, bringing the quantization procedure into twistor theory led you naturally to this holomorphic representation.
Yes. Well, yes.
So what happens then once you introduce that epsilon thing at the end of your lecture? In the commutation.
Oh, in the commutation rules, yes.
Yeah, what happens to that linkage between...
I think it depends on whether it's a real... I've got epsilon and epsilon bound. It may depend on whether that's a real number or not. I haven't really thought about it much. But certainly I think it's a real number. I mean, you certainly get this relationship between holomorphicity. I really shouldn't talk about that at the moment, because I fiddled around with it for a bit, without convincing myself it works or doesn't work. So, I mean, it works or doesn't work in the sense of being obviously inconsistent or something like that. I couldn't see any obvious inconsistency. I did fiddle around with it for long enough. But as far as I can see, it would not spoil the holomorphicity, so I want to keep that. Actually, it's a good question, because in a sense you want to spoil holomorphicity.
Well, that was sort of behind my question. Where do you ultimately, because you've written extensively about the role of measurement and non-unitarity in measurement and so on, which you link to gravitational process. So maybe at some stage you do want to.
You have a good point there. But certainly if you want the border rule, but you see, it's a statement about probabilities, and I'm not too sure about whether that has some kind of holomorphic relationship too. But it's certainly true in the conventional formalism of quantum mechanics. One place where you really need to go non-holomorphic is in the border rule. So you say, okay, you take the norm, you take the ratios of magnitudes, and but that's to get you a probability. And so whether that notion of a probability is something which comes in indirectly through things which remain holomorphic, I don't know. But it is a good question. Yeah.
Anybody else? No? Oh, sorry, I beg your pardon.
The way that you produce your objective geometry using coordinates rather than differentials makes me worry about translation invariance.
Oh no,
it's all completely
yes.
in.
Yes. No, that's just
symbolically.
You say you're allowed to do linear transformations on the coordinates, but you might want to preserve that Hermitian form.
They're all form invariant. Your equations are all form invariant.
Yeah, that's right. Yes, in fact, if you put that form in, then you get the group. What is it? The SO2C. No, U22, or SU22. Yeah, SU22. Which is the conformal group. Yeah. So it is one of these Cartan correspondences. That you get it's 014, 024 or SU22. So you have a local isomorphism between these groups.
I'm reassured.
Yeah.
Well done. Glad you're reassured, mate.
Sorry?
It's all coming out of the
Oh, sure, absolutely.
Right, are we done? Right, well, thank you very much.